This video is on section 5.3 notes, the graphs of sine and cosine functions. So first what I wanted to do is review, this is from section 2.3 actually, so back in Math 171, and there we talked about parent functions and transformations of parent functions, and we learned that a number in the front, a coefficient, would stretch a function. It would also compress a function, which would make the function tall and skinny or short and fat, and it would reflect the function over the x-axis. We learned that this h value would shift the function to the left or to the right, and that this k value would shift the function up and down. And all of those things are to be true when we look at sine functions and cosine functions, but they look just a little bit differently. And if you took me for your Math 171 course, then I taught you how to do all of these things algebraically, and we would write tables for each of the functions, and then we would shift the function left and right by adding and subtracting values to the x-coordinate. We would shift a function up and down by adding and subtracting values to the y-coordinate. Stretch or compress a function by taking its y-coordinate and multiplying it by that coefficient, that a value. We would reflect a function across the the x-axis by taking that y-coordinate and multiplying it by a -1. So all of those things that we did algebraically to points in Math 171, all of those things still work. They're still mathematically true. And if you were to start with a table of values, you could still do them that way. From my teaching experience, what I have learned is that most students tend to work best with sine and cosine functions if they work with them graphically or visually instead of algebraically. So all of these things are still true, but I'm going to teach you how to work with the transformations in a visual way as opposed to doing it this way. Now, if this way really resonated with you, if that's how your brain works, and you want to use these methods from this table we're about to fill out, that's totally fine. And it would be very calculator heavy. It'll be very computation heavy as you do these problems. And you are more than welcome to do that and then check how you do the graphs against how the video does the graphs and just make sure you're graphing them correctly. All right, because it's still mathematically accurate to do it that way. All right, so for the rest of us, if we're going to do it visually, this is how we would graph sine and cosine functions. So first, we're going to start with the sine function, and here we have written down some values from the unit circle that are going to make graphing sine pretty easy for us. So you'll notice that we've only written down the coordinates from the quadrantal angles. So I have 0 degrees is 1, 0, pi halves or 90 degrees is 0, 1, pi or 180 degrees is -1, 0. 3 pi halves is 0, -1, and then 2 pi is 1, 0. So sine of the angle measurement is always going to be the y-coordinate. So sine of 0 is just 0. Sine of pi halves is 1. Sine of pi is 0. Sine of 3 pi halves is -1. And sine of 2 pi brings us back to 0. And what I did for all of my notes pages is I went ahead and drew the axes in already just to save myself some time. And so I drew on most of these, I drew the x-axis right in the middle, and then I drew the y-axis on most of them 8 boxes over. And I'll explain more about that in a little bit. There's a couple problems where I didn't do 8 boxes, but I'll explain my line of thinking there. So for this particular graph, we're doing the parent function for sine. I'm just going to count 1, 2, 3, 4 boxes and put a pi, and then 2 pi, and then 3 pi, 4 pi, 5 pi, and 6 pi, and then I'll go backwards, -pi, -2 pi. And then on the y-axis, I'll just do 1 and 2, 1 and 2. And so if I graph a sine graph, when the x value is 0, the output is 0. When the x value is pi halves, the output is 1. When the x value is pi, the output is 0. At 3 pi halves, it is -1. And then at 2 pi, we have 0 again. Okay, so this is kind of just the perfect example of a sine graph. When you say sine, this is what people normally picture. Now, we know that for each of these angles, 0 and pi halves and pi and 3 pi halves, that we have coterminal angles, which means that this is 2 pi, but it's also 0. It's also -2 pi. It's also +4 pi, +6 pi. And the same thing for all of these angles. They are multiple angles. So what I'm going to do is I'm going to keep going around the circle and finding coterminal angles, which will allow me to continue to graph. So 2 pi left me at 0. And then we would have, what would that be? This is 4 pi halves. This would be 5 pi halves. So 5 pi halves would be at 1. And then 6 pi halves, or 3, would be at 0. And then 7 pi halves would be at -1. And then 8 pi halves, or 4 pi, would be back at 0. And then 9 pi halves would be back at 1. And then we'd be back at 0. And then -1. And then 0. So here is how I typically think of my visual cues when I'm drawing a sine graph. I only picture this part, and I say that the sine graph begins at 0 and it ends at 0, and it hits 0 in the middle. So I start off drawing all of those first. So if I'm going to draw one more cycle of this, I'm going to say it begins at 0, it ends at 0, it hits 0 in the middle. And then between the first two zeros, it goes up to 1. And between the second two zeros, it goes down to -1. So between these two, it goes up to 1. Between these two, it goes down to -1. And that's how you draw your sine curve. So on the next page, we have some vocabulary terms. So here they have the transformed sine wave. It's got the A in the front. They don't use the H and the K in this textbook for sine and cosine curves, but it's the same idea. So they put A in the front. That's like your vertical stretch or vertical compression, but it has a different name for this unit. B is a value that we haven't seen before. That's pretty specific to this unit. The C is kind of like the H value. This is what shifts the graph to the left or to the right. And then the D is kind of like the K that we've seen before. That's what shifts the graph up and down. So here are some vocabulary terms that are very specific to trig functions. Trig functions are periodic functions, which is a function that repeats its values at regular intervals. So this is the wave. It's making a wave, and it's repeating its values. An amplitude is what we think of as vertical stretch or vertical compression. So it's how much taller than normal the graph typically is. An amplitude of 1 is typical. If we had an amplitude of 2 or 3, that would mean that the graph had been vertically stretched. If we had an amplitude of 1/2 or 1/4 or 2/3, that would mean it had been compressed. The amplitude is found by looking at the distance between the center line and the peak or the trough of a periodic function. So if you look back at what we just did, the amplitude is from here to here. And for the parent graph of a sine function, for a typical sine function, the amplitude is just a value of 1. And you look for it in the same place. You just look at the front of the function. When you write y equals sine x, you just look at the very front. If it says y equals 2 times sine x, then the amplitude is 2. If it's y equals 0.5 times sine x, then the amplitude is 0.5. So it's pretty easy to find. Next, we have the period. The period is the horizontal distance over which a periodic function repeats its pattern. So here we said that this part was kind of like the perfect example of a sine graph. And so the period of a sine graph was just that whole circle that it took us to go from start to finish. So the period of a sine graph is 2 pi if it hasn't been adjusted at all. A cycle is one complete pattern of a periodic function. So this is one cycle. So from here to here, this is one cycle. So that's one cycle, a second cycle, a third cycle, a fourth cycle. Typically, the instructions will often say to draw 2 cycles when you're drawing a graph to make sure that you understand how to draw it. So you're drawing the first one and then continuing the pattern. The frequency is the number of complete cycles a function completes within a specified interval. So if we change the period of the function, then it would be interesting to say, well, if I've adjusted the period and it's no longer 2 pi, then how many cycles complete from 0 to 2 pi? Then that would be something we're interested in, and we'll see that in some of our example problems. A phase shift is just horizontal displacement, so it's just going left to right. So that's something new. We haven't called it that before. The midline is the horizontal line that sits exactly halfway between the maximum and minimum values. And so that's your like middle right here. And they don't often ask you to find it, but it's really helpful for application problems, for word problems. So that is the midline right there. And I wrote on the other page, so but that's the midline. Okay, so let's go ahead and do some example problems. One thing we need to know is that the period of a function is 2 pi divided by the b value. So 2 pi is normal. If you have a number in front of x, then it will shorten or lengthen that natural period of the periodic function, or in this case, sine or cosine function. So here, a normal period of the graph is 2 pi, and so we're going to say that the new period of this graph would be 2 pi divided by 2. And the period is directly related to the frequency, and I'm going to show you that on this one, how that works. So for each of these examples, they're asking us to find some of these different things. Find the amplitude, find the period, the frequency, the domain, and the range. The amplitude and the period are going to be important to find first because they're going to help you draw a picture of the graph. So the amplitude here is 1 because there's not another number in front of this telling us that we should have a stretch or compression with this graph. And so 1 is just typical. The period of the graph is 2 pi divided by the b value. The b value is what is in front of the x. So we have 2 pi divided by 2, which is just pi. The frequency, we can see here, it's just the b value. If you're looking at 0 to 2 pi, if that's the period that you're looking at, then it's just the b value. So we'll see that in a second. And then they want us to find the domain and range. The domain for these graphs is always going to be pretty easy. They make a wave. And then they just follow that wave forever. So they go forever to the left, forever to the right. So domain is always negative infinity to infinity. The range is always going to be bouncing back and forth between 2 numbers. So a typical sine graph is bouncing back and forth between +1 and -1, but a graph could be something else depending on what the amplitude is and if it's been shifted up or down. Okay, so here's how we're going to draw this graph. We know that the period has changed to pi, so if we were drawing a regular sine curve, we would start the graph at 0 and end the graph at 0 at 2 pi. And then we would have 0 in the middle. So this graph, since it has a period of pi instead, we're going to start the graph at 0 and we're going to end it right here. start the graph at 0, end the graph at 0. And then we're going to have the graph hit 0 right in the middle. So for sine, every time start at 0, end at 0, cross 0 in the middle. And then between the first 2 points, we go up to the amplitude of 1. Between the second 2 points, we go down to the amplitude of -1. So one of the reasons that I go by 8 boxes for 2 pi is because whenever I draw a sine curve, I always want to take something, I've got the whole thing, I divide it in half to put the 0, and then I divide it in half to do the amplitude again. So what numbers divide in half twice? 4 can divide in half twice, 8 can divide in half twice, 12 can divide in half twice. And so those are the numbers that I use when I think about how far apart the period of the graph should be. So over here, I let the period of the graph be 8 boxes. Here I used the same scale and the period of the graph was 4 boxes. So I'm just going to make sure whenever I draw this that the period of the graph is either 4 boxes or 8 boxes or 12 boxes, and that is pure laziness on my part. It's because it's easier to draw. Okay, so there is 1 cycle right there, and then I'm going to do it again. So beginning and end, there's the middle. Between the first 2, I go up to 1. Between the second 2, I go down to -1. And since I only have to draw 2 cycles of the graph, I'm just going to leave it like that. So the range of this graph is from -1 up to +1. And so I'll write that on here. -1 to +1. All right, for this next function, we have an amplitude of 2. So there's a negative in the front that tells us that we're going to start the graph upside down. But the 2 tells us we have an amplitude of 2. The period of the graph is 2 pi thirds. The frequency of the graph is 3. It's just the b value. The domain is always going to be left forever and right forever. And then the range I'll find in a minute. I forgot to talk about the frequency on this one. So if we go back, what you'll notice is that we changed the period of the graph to pi instead of 2 pi. And so now the graph from 0 to 2 pi completed 2 cycles. So that's what the frequency means. 2 cycles from 0 to 2 pi. The original function completed 1 cycle from 0 to 2 pi because x did not have a coefficient. So this has 2 cycles from 0 to 2 pi. Okay, the next one we draw, this one's going to have 3 cycles from 0 to 2 pi. All right, so on this one, I went ahead and I drew out my 8 boxes here, but I haven't labeled them yet. So I want to make sure in here that I label this in such a way that I can have an amplitude of 2 pretty easily. And I don't have to shift the graph up or down at all. And so I'm going to go ahead and do 1, 2, 1, 2, like I did with the other graphs. And so this graph is just going to be taller. And then for the period of 2 pi thirds, I'm just going to make sure that 2 pi thirds is either for 4 boxes or 8 boxes or 12 boxes, and it doesn't matter which one you do. So I'm just going to count 4 boxes and say that that's pi thirds, and another 4 boxes and say that's another pi thirds. So 1 pi thirds, 2 pi thirds, 1 pi thirds, 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds, and then 6 pi thirds. Okay, so to draw this graph, I start at 0 and end at 0 for the period. So start at 0, end at 0. And I hit 0 in the middle. And then normally between the first two, we go up to 1. That's normal. Now with this one, we have an amplitude of 2. So the amplitude of 2 would tell us to go up to 2 instead of go up to 1, except this graph is upside down. So between the first 2 points, I'm going to go down, and I'm going to go to 2 because their amplitude is 2. Normally between the second 2 points, I would go down to 1, but instead I'm going to have to go to 2 because this is an amplitude of 2. And because the graph is upside down, I have to go in the opposite direction. So instead of going to 1, I'm going to go to 2 for an amplitude of 2, and I'm going up because it's upside down. So beginning, end, there's 0. I'm going to go down to -2 to show that it's a negative graph with an amplitude of 2. And then I'm going to go up to +2 to show that it's a negative graph with an amplitude of 2. Beginning, end, in the middle, -2, +2. And here you can see the period of the function, right? There's the 2 pi thirds, there's 2 pi thirds, there's 2 pi thirds, and you can see that frequency of 3. Here's 1 cycle, 2 cycles, 3 cycles on the interval from 0 to 2 pi. This whole thing was 0 to 2 pi. So we got 3 cycles on that interval. All right, let's go ahead and look at this page. So here we have an amplitude of 3. We have a b value of 1/2. X divided by 2 is the same as 1/2 times x. So I'm going to say the period is 2 pi over b. So it's 2 pi divided by 1/2. Whenever we have something like this, if you have something divided by a fraction, you do 2 pi, and then you multiply it by the reciprocal of that fraction. So 1/2 I'm going to do multiply by 2 over 1, and so this gives me 4 pi. So 2 divided by 1/2 is 4. The frequency is 1/2. So from 0 to 2 pi, we're going to see half of a cycle. And then we've got the domain. I just realized I didn't do the range for that previous problem. Let me go ahead and do that now. So this problem right here, the range is from -2 to +2. -2 to +2. Okay. All right, so for this one, domain is -infinity to infinity. And then we're going to write the range at the end of the problem, hopefully, if I remember it. Okay. So for this one, we have, I already filled in the same horizontal intervals. They seem to work pretty well for this problem. For the y-axis, I didn't want to go 1, 2, and 1, 2 because I had an amplitude of 3, and then I have to shift the graph up 1. And so that wouldn't leave me enough space. So this time I decided to go 2, 4, and 2, 4, so that I can draw an amplitude of 3 to start with, and then when I'm done with that, take the graph and shift it up 1. So to start with, I'm going to ignore the +1 on the end, and I'm just going to work with the amplitude and the period. So those are the first 2 things that you can always graph. They're the easiest to work with. And then after that, if you have to shift the graph to the left or to the right, or shift it up and down, you can do that next. So the period is 4 pi, so I'm going to start at 0, end at 4 pi. That means I have 2 pi in the middle. Between the first 2 points, I'm going to go up to the amplitude. So normally I'd go up to 1, but in this case I'm going to go up to 3. So go up to the amplitude. Between the second 2 points, I'm going to go down to the amplitude. And so this would be ready to draw, except now I have to take all the points and shift them down 1 unit. And be careful when you're doing this because a lot of times 1 unit isn't necessarily 1 box. So be careful when you start to shift your graphs left or right, up or down, to know whatever number you're shifting it, how many boxes that should be on your graph paper. So here, shifting it up 1 is 1 box. And so that works out nicely for this problem. And whenever I do these, I just put an X through the previous version. That's kind of like me showing my work. So we only got half here, so I'm going to draw half. Now, the instructions do say to draw 2 cycles of the graph, and we're going to be able to do it on this one, but typically when you're doing some of these more stretched out graphs, when they start to get a little funky, it might be harder on these graphs to have enough space to do that. So I'm okay with you having less than 2 cycles, just so long as it's not on every single problem. So try to draw 2 cycles if you can. If you miss 2 cycles on a couple, that's not a big deal. Okay, so here's our graph. The range here is from -2 up to 4. All right, for this next one, we have an amplitude of 2. And then this is the first graph that we have a phase shift on. And so we have to be really careful here. And I would highlight this in my notes if I was you, because this is something that students do incorrectly often. So they would think, okay, this graph has a b value of 2, so I'm going to find the period of the graph, and they can do this part correctly. They'll say, okay, the period is 2 pi divided by 2. The period is pi. That's true. And then they'll say this graph has been shifted to the right pi halves, and that is not true. So if we were to look back at our notes, the second page of our notes, we'll notice that the second page of our notes puts the b like this with parentheses around x minus c. It means that the coefficient of x actually has to be factored out for us to see how the graph shifts to the left and to the right. So this has to be factored, and oftentimes it's not. So be really careful about that. That's something that's really easy to miss. So here I'm going to have to factor a 2 out of pi halves. So I'm going to say I have y equals -2 sine, and I'm going to factor a 2 out. Pi halves divided by 2 is pi fourths. So this is pi fourths. Another way to think of it is you want to make sure that if you multiply 2 times 1/4 is going to give you 2/4, which is going to bring you back to 1/2. Okay, so this is what we're graphing. We're going to do a phase shift, is what this is called when you shift the graph left or right. We're going to do a phase shift of moving the graph to the right pi fourths. Okay, so the period is pi. The frequency is going to be the b value, and that's 2. The domain is -infinity to infinity, and I'll find the range later on. Okay, so since I know that I'm going to have to shift the graph to the right pi fourths, I want to keep that in mind when I set up the interval along my horizontal axis. I just want to make sure that shifting to the right pi fourth is something that's going to be easy to do. And on this problem, it is if I go by 4s for the period of the graph. 4 boxes, right pi fourths, that's going to be pretty easy to do. So this kind of default that I've been using is actually going to work really well. For the amplitude of 2, I could do 1, 2, as I've been doing for a lot of the graphs, or I could do 2, 4. It doesn't matter. It's just going to make my graph look different compared to other people drawing the same graph. So it really doesn't matter. It's just if you're comparing answers with another person that it would make a difference. So I'm going to go ahead and just do 1, 2. I can draw an amplitude of 2. I don't have to worry about shifting it up or down. I'll have enough space. So I'm going to go ahead first and graph just the amplitude and the period, and then after that I'll shift the graph to the right. So I'm going to start by going from 0 to pi with 0 in the middle. And then I have to do my amplitude of 2, and I have to draw this as a negative graph. So amplitude of 2 with a negative graph. So down to -2 between the first 2 points, and then the second 2 points, an amplitude of 2 with a negative graph means I'm going to be going up. So these are my points here. And then from there, I'm going to shift all of the points to the right pi fourths, which is 1 box. So I'm going to shift this 1 box to the right, 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 1 box to the right. Whew. My drawing isn't very nice this time. Okay. And then I can keep up the pattern. I'll let that be enough. There we go. Okay, so this graph had a range from -2 to +2. All right, for this last sine example, I purposely made things a little bit more complicated so that you guys could see when we would need to be really deliberate about how we draw the interval. So first with this one, we'll go ahead and write down our information. I can see that the amplitude is 1. And for this one, the b value is actually 1, and so the period of this graph is just 2 pi. Or you could say 2 pi divided by a b value of 1 means that the period is just 2 pi. And since the b value is 1, that means the frequency is 1. So we're going to see 1 full cycle from 0 to 2 pi. And the domain is going to be -infinity to +infinity. And then the range we'll do in a little bit. So on the surface, this graph seems like it would be a little bit easier because it has just the standard amplitude and the standard period. What makes this graph a little bit more difficult to draw is that it has a phase shift of pi thirds. So if I count, like this graph, 4 boxes and write pi, then shifting to the left pi thirds is going to be difficult because it's not going to be a full box. Or if I count 8 boxes and count 8 boxes as pi, that's going to be difficult because pi thirds is not going to be a whole number of boxes. So what I said earlier on in the video that I like to do sets of 4, 4, 8, or 12. This is one where I would do 12 boxes for pi because then pi thirds would be a specific number of boxes. So I counted out 12 boxes here. 12 boxes is 1 full pi. So if I do 1 full pi divided by 3, 12 boxes divided by 3 is 4. So 4 boxes is pi thirds. 4 boxes is pi thirds. And this is one that it actually goes off the page, and it works out fine since we're going to have to shift it to the left. So I went ahead and just let it go off the page. So 12 boxes is pi, and then I just counted, and every 4 boxes I did 1/3, 2/3, 3/3, 4/3, 5/3, and then 6/3. I had to make sure I went all the way to 2 pi because this is one period of the graph. And one period of the graph is how we draw a sine curve. So I'm going to put my dot to start with at 0, and there's my ending dot at 0, and then my middle dot. And then between the first 2 points, we normally go up to an amplitude of 1. And so right in the middle, I'd go up to 1, except this is a negative graph. So in the middle, I'm going to go down to -1. And the middle is going to be right in here. And if you need to count 6 boxes in the middle, you can. And then between the second 2, I have to go up to +1. So right in the middle, I'll go up to +1. Okay, and then each of these points is going to need to move to the left pi-thirds, which is 4 boxes, and then go up 1, which is 2 boxes. So I'm going to go left 4 boxes and up 2 boxes. Left 4 boxes, up 2 boxes. Okay, so here is one full cycle, and then I can kind of, this is 2 and then 6, so 2 and then 6. So hard to draw much more than that. The range is from 0 to 2. Okay. One thing I want you to notice, and this will come into play when we do some of the application problems, is that if you look at the midline of these graphs, you can see the midline in the equation. So here's the middle, that horizontal line that cuts through the graph. Here's the midline, it's at 1, and it matches the +1 on the end of the equation. For this graph, the midline is at 0, and that's because there is 0 on the end of the equation. There's no number there. Here, this graph, the midline is at 1, and that's because of the +1 on the end of the equation. And so that's something that's important to notice about these graphs, is that you can see the midline in the equation itself. Okay, next we're going to look at some cosine graphs. So I'm starting with that same information from the unit circle. I know that cos is the x-coordinate. I'm still going to look at the quadrantal angles, and I can still see that my outputs are going to be the same. I'm still going to be graphing zeros and ones. I'm just going to be graphing them in a different order. So this time, the 0 radians or 0 degrees is going to give me an output of 1 because I'm going to be using cos instead of sine. So it's going to give me an output of 1. That's where I'm going to start. And then pi halves is going to give me an output of 0. Pi is going to give me an output of -1. 3 pi halves is going to give me an output of 0. and 2 pi is going to give me an output of 1. And so this is what a cos graph looks like. And until we do another cycle of it, you don't really recognize it as being the same as a sine curve, even though we know it is because we're still repeating the same values. So if I continue to do more cycles of the graph, then I'm going to have 0 next, and then -1, and then 0, and then +1. Where to go? 0, and then +1. And so now we can see that same wave as a sine curve. It just started in a different position. So when we draw the cosine curve, we're going to start up at 1 and we're going to end up at 1. In the middle, we're going to dip down to -1. And between these two ones, we have to cross at 0. Between these two ones, we have to cross at 0. But we're going to see that same periodic wave that we saw with a sine curve. So we're going to start up at 1, we're going to end up at 1. In the middle, we're going to dip down to -1. And then we have to cross over at 0 and cross over at 0. And that's how we create our cosine curve. And so we think of this part as being the cosine curve. This is one cycle of the cosine curve. And when people see just this portion of the drawing, that's how they think of a cosine curve as looking, even though in reality a cosine curve and a sine curve look identical to each other if you were to back up and look at the whole picture. In fact, if I were to take this drawing and start right here, then I would say, oh, that looks like a negative sine curve. It just starts down and then goes up. Or if I were to start right there, I'd say, oh, there's the sine curve. So really, a cosine curve is a sine curve with a phase shift. It's a sine curve that's been shifted to the left or to the right so that it starts in a different spot. So a cosine curve is a sine curve with a phase shift. And the phase shift, the amount of the phase shift depends on what the period of the curve is. So for a normal period of the curve, it would be exactly 3 pi halves that it's been shifted to the right to get you started with a positive sine curve, or it would be pi halves shifted to the right if it was a negative sine curve. So it's been shifted if you're thinking of it in terms of a sine curve. All right, so let's go ahead and look at some cos graphs and draw a couple cycles, and we'll find all the same information. So this will be a little bit easier now that we've already worked with the sine curves. So this says 0.5 cos times cos of 4x. So the amplitude is 0.5. The period of the graph is 2 pi divided by 4, which is pi halves. That means that the frequency of this graph is 4. So from 0 to 2 pi, we're going to see 4 cycles of the curve. The domain is from -infinity to infinity. All right. So for this graph, since it's 0.5 for the amplitude, I went ahead and just did my typical y-axis intervals. I thought that would work just fine. Since the period of the graph is pi halves, I didn't want to do 4 boxes as pi because that would make what I have to draw as a full cycle of the graph in 2 boxes, and I always want a full cycle to be in 4 or 8 or 12 boxes. I want something that I can divide in half and then divide in half again, and it would have been a little bit too squished if I used 4 boxes for pi. So I'm going to use 4 boxes for pi halves for this one. And I'm going to count pi halves, pi, 3 pi halves, 2 pi, 5 pi halves, 3 pi. Okay, and so with the cos graph, that means typically I would start up at 1 and end up at 1. But in this case, because I have an amplitude of 0.5, I'm going to start up at 0.5 and end up at 0.5. So using the period of my graph, I start at 0.5, I end at 0.5. In the middle, I dip down to negative 0.5. And then between these two, I have to cross 0. Between these two, I have to cross 0. So there is one cycle of the graph. And then I just have to keep doing that. So start at 0.5, end at 0.5, dip to negative 0.5 in the middle, cross 0, cross 0. Start at 0.5, end at 0.5, dip to negative 0.5 in the middle, cross 0, cross 0. And I can do it again so I can see that frequency. Okay, so here's 1 cycle, 2 cycles, 3 cycles, 4 cycles from 0 to 2 pi. So I can see that frequency of 4. The range is from negative 0.5 to positive 0.5. So I'll go ahead and write that down. All right. For the next one, we have negative cos x divided by 3 plus 2. So on this one, we have an amplitude of 1. The period is 2 pi divided by 1/3. X divided by 3 is the same as 1/3 x. And so that means that the b value is 1/3. So to calculate this, I'm going to say that this is 2 pi multiplied by 3 over 1. Because when we divide by a fraction, we multiply by the reciprocal. So this period is 6 pi. The frequency is 1/3. So from 0 to 2 pi, we're only going to see 1/3 of a cycle. And the domain is from negative infinity to infinity. So for this one, you could have left the x-axis right in the middle and just used each of your boxes, allowed each of your boxes to be 1 when you drew your interval. Or if you did what I did, then you could say, well, if I have an amplitude of 1 and I'm going to shift the entire graph up 2, then for me to have the space to do that, I needed to shift my x-axis down on the grid so that I could have an amplitude of 1 and then still shift the graph up 1, 2, and then it's going to end up here. So either way, you could have put the x-axis in the middle and just had one box equal 1 for the interval. And then as far as the period goes, I want to make sure that when I count for 6 pi, I'm either having 4 boxes equal 6 pi, 8 boxes equal 6 pi, or 12 boxes equal 6 pi. I opted to just have space to have 8 boxes equal 6 pi. All right, so for this negative cos graph, that means we're going to work upside down. Instead of starting at +1 and ending at +1 for the end of the period, we're going to start at -1 and end at -1 for the period. And then in the middle, we're going to pop up to +1. And then between those ones, we have to cross at 0 and cross at 0. All right. We don't have a phase shift. We don't have to shift left or right, but we do have to shift up 2. And in this case, 2 shifting up 2 would be shifting up 4 boxes. So for each of these, I'm going to move up 4 boxes. Up 4 boxes. Up 4. Up 4. Up 4. And then I can just follow that pattern. Was kind of nice. Here we go. Okay, so from 0 to 2 pi, somewhere in here, we only get 1/3 of the cycle. So not very much of it. The range for this particular graph is from 1 to 3. All right, we are almost done. I know this video is terribly long, and I'm sorry. The graphs are just, I want to make sure you guys had enough examples to truly understand it. Okay, this last one, I'm making it a little bit funky on this one. I gave you guys a B value that had pi in it. It happens every so often. And so here we have an amplitude of 2. That's pretty easy to work with. The B value with the pi in it is pretty weird. So with this, we have to make sure we factor this. So we're going to say 2 cos pi over 6 factored out. That's a plus. So for this, we have to do pi thirds and divide out the pi 6. And so I'm going to say pi thirds divided by pi 6. That's what we're figuring out for this part right here. And whenever I divide by a fraction, I just multiply by the reciprocal. So times 6 over pi. The pi's cancel. And we get 6 over 3 is 2. So this graph shifts to the left 2. Nothing in terms of pi, it just shifts to the left 2. The period of the graph is 2 pi divided by b. The b value is pi over 6. So we're going to do the same thing right here. We're going to take 2 pi. We're going to multiply this by the reciprocal. So multiply by 6 over pi. The pi's cancel. And the period of this graph is 12. Not 12 pi. Nothing in terms of pi. Just literally just the number 12. The frequency of this graph is pi over 6, whatever that happens to be. 3.14 divided by 6, about 1/2. So we're going to see about 1/2 of a cycle. 1/2 of a cycle from 0 to 2 pi, so 1/2 of a cycle from 0 to 6, approximately. The domain is -infinity to +infinity, and then the range we'll get at the end. Okay, so here, since the period of the graph is 12, I went ahead and just put 12 boxes right here. And so we're going to have 2, 4, 6, 2, 4, 6, 2, 4, 6, 4, 6, 2, 4, 6. Okay. And then here we have an amplitude of 2, and we're going to shift down 1. So I can't do 1, 2, and 1, 2. If I do that, I'll have room to draw the amplitude of 2, but I won't have room to shift down 1. So I'm going to have to count each box as 1. So I have room to draw the amplitude of 2, but then also room to shift the graph down 1. All right, so this is a positive cos graph with a period of 12, positive, and it has an amplitude of 2. So I'm going to start up at positive 2. I'm going to end at positive 2. In the middle, I'm going to dip down to negative 2. And then between those, I'm going to cross at 0. So cross and cross. Okay. Now, each of these points need to go left 2 and down 1, however many boxes it takes to do that. The horizontal boxes, they're just each are worth 1. The vertical boxes are worth 1 as well. So for me to go left 2 and down 1, I literally am just going to go left 2 and down 1. So, but always be careful because that's not how every single graph has been. So you're going to need to think it through every single time. Okay, so um, so I'm just counting almost like a slope. I can see 3 boxes and 2, 2 boxes, 3, 2, 3. I can just see that it's kind of a horizontal movement of 3 boxes and then a vertical movement of 2 boxes. And that's how I'm drawing the rest of this and following the same pattern. This particular graph has a range from -3 up to 1. All right, we are almost finished. So let's get on to these last couple question types. So your textbook defines frequency as the frequency f of a sine wave. And when they say sine wave, they mean sine or cosine. With a period p, sorry about that, with a period p, is defined by frequency equals 1 divided by p. And so when they do this, you'll notice that they haven't mentioned anything about on what period of the graph or what interval of the graph are we talking about. I always specified we were talking from 0 to 2 pi. And what I noticed was when I looked at the example problem in the textbook, the example problem didn't specify an interval either. So when our textbook uses this formula, the sine wave completes p cycles, whatever the period is, p cycles on the interval from 0 to 1, or 1 cycle per the interval from 0 to 1 over p. So this is, I'm giving it to you. You're going to have to always refer to this because whereas I would have expected it to give you an interval, it just doesn't. Okay, so here it says find the frequency of the sine wave given by this equation. And so this has a b value of 524 pi, and what they've done is they've given you something that would be almost impossible to graph, or impossible for you to graph on a calculator and visualize with your naked eye, and then especially not to be able to look at it and count the number of cycles. So we have to use the formulas on this. So we're going to say the frequency is 1 divided by the period, and to calculate the period, we do 2 pi divided by b. 2 pi divided by the b value, which is 524 pi. Okay, so here the pi's are going to cancel out. 2 over 524 is going to reduce. 2 goes into 2 one time. 2 goes into 524 262 times. Okay, so now I've written it as 1 over p. So this means that this is our p value. This is our period. Well, the period of the graph is 1 over 262, but this is the p from the formula. Okay, so it is p cycles, so 262 cycles on the interval 0, 1, or 1 cycle on the interval from 0 to 1 262nd. That's 2 ways for you to say the frequency if they're not asking about a frequency from 0 to 2 pi. So that's just a little trick. At the time I made this video, I'm not sure if I'm going to assign any of these problems yet. So, so I just thought I'd give you an example so that you can compare it. Pretty easy to do, but you definitely have to have this written down or else it'd be easy to forget. Okay, so next we're going to look at an application problem like this where they have information they've given us that is periodic, and they're going to ask us to write a function equation that would work for that information. So it says 10 minutes after a furnace is turned on, the temperature in a room reaches 74 degrees and the furnace turns off. It takes 2 minutes for the room to cool to 70 degrees and 2 minutes for the furnace to bring it back to 74 as shown in the following table. So you have this kind of periodic cycle here where it goes 74, 72, 70, 72, 74, 72, 70, 72, 74. So the temperature is going up and down, up and down. So first I'm going to draw a picture of this information so I can appreciate what it looks like and see that periodic cycle. And it doesn't need to be scaled perfectly, but I want to see the 70, the 72, and the 74. So we're starting here at 10 minutes, and I'm going to just do a few of them. So 10, 11, 12, 13, 14, 15, 16. We'll see how far I need to go. So 10 is at 74. 11 is at 72. 12 is at 70, and then 13 is at 72, and 14 is at 74. Okay, I didn't do a perfect job drawing it, but it looks something like that. Okay, so we're just going to start writing some information down that we know shows up in our equation. So we're going to have either y equals a times sine b x minus c plus d, or y equals a cos b x minus c plus d. So they said to write a sine function, so maybe they'll tell you to write sine. Oftentimes they'll let you choose which one. In up here for kind of the title of this section, it says sinusoidal. If they say write a sinusoid, if they use that whole word, they're talking about sine or cosine. So a lot of times when they say sine curve, it's sine or cos, and you could do either. So keep that in mind. I am going to show you how to write both of them, even though the instructions do say sine, because they're very similar. So when we look at this, one of the first things that is always helpful to me is to draw the midline in there, because first of all, we know that that midline is the d value. Okay, so we know here that the midline is at 72, and so that d value is 72. That's actually in the equation. Okay, it's also going to help us figure out what the amplitude is. So from the midline up to the peak, or the midline down to the bottom of the valley or the trough, that's how big the amplitude is. And so the amplitude is 2. Goes up 2, goes down 2. All right. We also need to figure out what the period of the graph is. And the period of the graph is how long the horizontal distance it takes for there to be a complete cycle. So from here to here is one cycle of the graph, and so we want to see how much time that is. So that's from 10 seconds, 10, 11, 12, 13, 14 seconds. So a period of the graph is 4 seconds. Now, the calculation that is done to figure out the period of the graph is we do 2 pi divided by b, and we get 4 as an answer. That's how they would have calculated to get 4. And so we need to figure out what the b value is because it's the b value that shows up in the equation. So what I'm going to do is make this not a fraction anymore. I'm going to multiply the b over to the other side. So 2 pi equals 4b. And then I'm going to solve for b by dividing the 4 over. So 2 pi divided by 4 equals the b value, and 2 pi divided by 4 is the same as pi halves. So the b value is pi halves. So at this point, I think we are pretty close to being able to write our equations. So I'm just going to start them right here. If I wanted to write this as my equation, let's say I want to write this as a cos equation, then I'm going to call this 2 times cos. I'm going to put a b value of pi halves. And I'm going to put a d value of positive 72. This graph has shifted up 72. That's where the midline is. And all I need to figure out is how did they make the graph start here at positive 74 instead of starting on the x-axis at 74? Because this graph has been shifted to the right, and it's starting at an x value of 10, shifted to the right. So in here, I would just need to write x minus 10. So this would be a cos equation that would give me the information that I need. I can also write a sine equation that would give me the information that I need. If I start right here, this looks like a sine curve, but it looks like a sine curve that starts in the negative. It's going down first and then up. So if I wrote this, I could call this -2 times sine, and I would keep the b value the same. I would keep the 72 for the midline the same, and I would say that this graph shifted to the right to whatever number it is that makes the graph start right here. And I think that makes it at 11. It would have to start at 11, or it shifted to the right 11. So this equation would write it if I was doing a sine curve. Okay, or if I wanted to write this as a sine curve, but I wanted it to be a positive sine curve, then I could call this the start of the graph, and then I could write this as a positive sine curve. So y equals +2 sine pi halves. And then I would say that I'm starting right here. 11, 12, 13, and so x minus 13, I would say 13 is where I started the graph. And here's how you could check your work on a problem like that. I went ahead and graphed all 3 of the equations that I came up with, but you would graph whatever equation you came up with. And then I'm going to look at the table and compare it to the table right here. So if I look at the table, I can see that my inputs 10, 11, 12, they match. For all 3 equations I worked with, I got the same outputs. There's the third one. I got the exact same outputs I was supposed to have, whether it was the first, second, or third equation. So that tells me that I came up with the right equations for all 3. So any of these would be a correct answer. And if you're doing a problem like this, there is no singular right answer. There would always be several answers. And the difference between them would just be whatever phase shift you decided to write.